Okay, having polar codes and having shown that the channel polarizes, now we're going to look at decoding polar codes. So we have the basic construction of the codes. We know how to use polar codes for communication. And now we want to construct, after we've constructed, we want to decode the polar codes. So we saw, just to recapitalize what we have, we transmit frozen values, for instance zeros, on the synthetic channels where the erasure probability goes to 1 or the mutual information goes to 0. And we actually transmit our useful information on the channels that actually have a high mutual information or very low erasure probability. So how does the decoding work? Well, in the decoding, we need to undo kind of the construction. So we use this successive cancellation decoder by first decoding the channel gamma plus. Then using this result, we decode the channel gamma minus. So essentially, we serially and sequentially decode the individual channel transforms if we can do so. And for doing this, we exploit the knowledge of the frozen bit values inside the decoder. This essentially corresponds to a log likelihood ratio of plus infinity. And we're going to see that essentially we can reuse many of the operations from LDPC decoding that we already know, because we can interpret some of the operations as check not operations and some of the variable not operations. This decoder has a drawback, and the drawback is that parallelization is very difficult because we need to serially undo the different operations. We're going to see an example how to do so. And later we're going to see also a different view of the code and how to decode polar codes in a more parallelizable way. However, with some drawbacks in terms of performance. So first we're looking at the binary erasure channel, and we're looking at the decoding and the encoding. So here we have the polar code, and we use a simplified description. So here we have the additions, we have the basic transformations. Here's first basic transformation, here's the second basic transformation. Then we generate the channels gamma minus here, generate the channel gamma minus here. Then we combine the two channels gamma minus to generate a channel gamma minus minus and the channel gamma plus minus, or gamma minus plus, depending on how you do the counting. And we combine two gamma plus channels with a basic transformation to get channels gamma plus plus and gamma plus minus. So now we undo the operations. So here we have the channels gamma, and we receive y1 up to y4. So, and we have already seen how to undo the different operations. So we can undo the channel gamma minus. We have two received values, y1 and y2. And if both are not erased, so if y1 is not erased and y2 is not erased, then the output is y1 plus y2, and otherwise we need to output an erasure. That's how we undo the channel gamma minus, and that's the decoder D minus. So that's the decoder for the channel gamma minus. It's for the binary erasure channel. Keep it simple first. Then we undo the channel gamma plus. We have two inputs, y1 or z1, z2, and a known bit v1. So this is the known bit v1, and then we decode. So if z2, if the second input is not erased, we can immediately output z2. If the first output is not erased, then the second output is given by z1 plus v1. That's the second output. So if both are erased, none of this condition is fulfillable, and then we will output an erasure. But to do so, to decode gamma plus, we need V1. So we'll need V1. So let's ripple through and see what we can do. So we receive Y1, and we can immediately try to get V1 by decoding gamma minus. So we can decode gamma minus, we can combine Y1 and Y2, and we get an estimate of Z1. We have decoded gamma minus. Then we can do the same here. So we can decode gamma minus for this channel, and we get Z2. We don't yet have V1. We could make a hard decision here, but that's not going to work. So we don't know V1. We need to get V1 from this side by making these final decisions and rippling those final decisions through. We cannot make an intermediate decision because on the intermediate channels we don't do any coding. We only do the coding from end to end. So we cannot undo D minus here. So we have two channels D minus, and now we can try to decode U1 because we combine the outputs of the two D minus decodings to get U1. So we combine them, we do two D minus decoding, and we get U1 hat. So we get an estimate for U1 hat. So now what we do is either we have two options. First, U1 is a frozen bit. Then U1 hat equals the frozen value. Then we know that this channel is not reliable. So we know this channel is not reliable, and that means we will not use it. So then we just say U1 hat is a frozen value, then because we know the frozen value of the unreliable channel. Then the second option, U1 is not frozen. Then use U1 hat is equal to the output of D minus the individual inputs. If it is not frozen, with very high likelihood it's not erased, because that's an erasure channel with an erasure probability that's extremely small, close to zero. So with high likelihood it's not erased, so it will not be an erasure and it will be the correct value. In this case, it's not a reliable channel, it's most likely erased. So these are our two options. Interestingly, we get U1 hat. So now we have this channel transformation and we have U1 hat. So we can use U1 hat to undo the channel D+. That's what we do next. So we use U1 hat to undo this channel with the D+ decoder and get an estimate of U2. Again, same thing here. If U2 is frozen, so again, we have two options. Let me just write them quickly down. First one, U2 frozen. That means U2 hat is or becomes the frozen value. And second option, U2 is not frozen. Then U2 hat is the output of the decoder D+. And U1 hat is being used as an input to this second decoder. So now we have undone this output. So now we have U1, we have U2, so we can calculate V1. So now V1 hat is equal to U1 hat plus U2 hat. So we can calculate V1, and that means we can undo this channel as well. So we can do the D2 decoding on this channel as well. So that's what we do. We plug in V1 hat into the D plus decoder, and we get an estimate of Z3 that's over here. So now we can continue. So we have this guy. We have this guy decoded. We have this guy decoded. We have this guy decoded. And now we can continue with decoding this final channel, this one, because we need to have V3. V3 is nothing else as U2. V3 and U2 are the same. So we can decode this D plus channel by inputting V3 hat, but V3 hat is equal to U3 hat. Sorry, V3 hat is equal to U2 hat. There's a change of indexing here. So we can plug this guy in here, and then we can undo this decoding Z4, and we get an estimate over here. So we get an estimate of this variable. And then we have this one, so we can start undoing this operation. So we have a D minus decoder down here using the output from this channel here and using the output from this channel here. So we do this, we use a D minus decoding, and we get U3 hat. And with U3 hat, again, we check if it's frozen. If it's frozen, we use it. If it's not frozen, we use the frozen value. If it's not frozen, we use the output of this D minus decoder. And then we can use U3 hat to undo the D plus operation of this guy and get an estimate for U4. That's shown here. So we use U3 hat and then get an estimate of U4 hat. That's how you can do the decoding. So it's this successive decoding, and you need to successively ripple through everything. So it's the sequentiality depends a little bit how you can do it. So it's not trivial, but there is a very well-defined order here. And actually you can see the order if you have a bigger matrix, not only twofold repetition, you can actually see the order and then do the order in a very clear and well-defined way. So that's for the B.Sc. What do we do on the on general channels? So on general channels, we have the following situation. So we have U1, and then I'll put a box here together with U2. We saw that U2 acts as a noise, kind of. So we have the following situation. We transmit over the channel gamma. This is U2. We receive Y1 and Y2. And this is X1 and this is X2. And we have the condition that XU1 plus X2 is equal to X1. Or this is equivalent to saying that U1 is equal to X1 plus X2. So the first step now is we calculate log likelihood ratios, L of Y1 given X1. And we calculate L of Y2 given X2. So for instance, this is equal to 4 times ES over N0 times Y1 in case of a binary input AWGN channel. or you can use your favorite channel. And then the decoding of the D minus. This is nothing else as a check node. This is a parity check condition stating that U1 is equal to x1 plus x2. Or even another condition states that U1 plus x1 plus x2 must be equal to 0. So it's a parity check operation, and we know exactly what to do, how to decode a parity check operation. So D minus is as input L1 and L2. So this is equal to L1 and this is equal to L2. And the operation is 2 times the inverse hyperbolic tangent times the hyperbolic tangent of L1 divided by 2 times the hyperbolic tangent of L2 divided by 2. Or you can use your favorite approximation. So for instance, the sine of L1 times the sine of L2 times the minimum between L1 absolute value and L2 absolute value. That's the D minus decoder. So it's essentially a simple check node operation. So now we're looking at the second part, the D plus. So again, we have the same situation. And we should have a channel here. So we have V1 as an additional input over there. And this now acts as a variable node because it says that the messages along this edge is the same as the message along this edge, and it's the same as the message along this edge. So we know that a variable node essentially means the messages along the edges or the values along the edges are the same. This is the same thing that happens here. So this is a variable node. So we can calculate the outgoing message, this blue color, D plus here. D plus depends on L1, on L2, and on V1. And this is just L2. We take the log likelihood ratio of the second channel plus L1 times, and now we need to take care of the sign, -1 to the power VI. Why is this? If V1 is equal to 0, this has no effect. And here, this means so it means that Y2 or X2 should be the same as X1. If V1 is equal to 0, X1 and X2 are the same, and Y1 and Y2 should be the same. So we add the log likelihood ratios. If V1 is equal to 1, that means we change the sign here. So this message has the opposite sign of X1, or its binary is opposite of X1, because X1 plus its opposite will be equal to 1. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. So to get a 1 here, these messages must be opposite. So we need to flip the sign from its reliability. So that's why we have this sign flip. So that's the D plus decoder. So in here, this is where the D minus flows. So this is how you can actually implement the D minus decoder. And this is how you can implement the D plus decoder. So both very, very, very simple decoders. So this summarizes the functions. So we have the D- decoder and the D+ decoder. And then you have log likelihood ratios, and the final estimate UI hat is based on the sign of the incoming log likelihood ratio if it's not frozen. And otherwise, we need to use the frozen value. So, very, very simple. So here is an example of a decoder. And this is the bigger example. And we're going to look at what's going on here. So we have 4 frozen positions. U1, U2, U3, and U5 are frozen. And here we have the channel outputs, and we give some log likelihood ratios. Very, very simple log likelihood ratios. So first, we undo the channel D-. So we do D- channels, and we get these values over here. And these are equal by luck because here we use the same log likelihood ratios. So we execute D-. Then we combine these two D- and do another D- channel. So we do another D- channel over here. We do another D- channel over here. Then we combine those, do another D- channel over here. And we get a log likelihood ratio that's 0.19. This is very unreliable. This is not something you should make a decision upon, because this says it's 1 with probability 1/2 more or less. But we don't care because this is a frozen value. So we can say U1 hat is equal to 0. So we know U1 hat. And now we undo the D+ decoding. In this case, because U1 hat is equal to 0, it means we need to sum up these two log likelihood ratios. So 0.63 plus 0.63, and we get the value D+ for this guy. So we execute D+, we get +127. Again, this is a frozen position. So we said U5 hat is equal to 0. Okay, so now we have this frozen position. So we can undo the channel D- over D+ over here. So we get minus 3.42 over there. Then we continue. We have these two channels. They are combined. We have the two outputs. Now we can do D+ decoding of these two channels. So we do D+ decoding. We get this value. It starts to get a little bit more reliable, but it's frozen. So we don't care. We throw away. And U3 hat is equal to 0. So now we have U3 hat. Now we can undo D+. So D+ is equal to minus 3.42 minus 3.42. We don't make a sign change because here we have a 0. So we get minus 6.84. So minus 6.85 because of rounding effects. I cut off after two digits behind a comma. So we have minus 6.85. And this gives us U7 hat. So we have U7 hat is equal to 1. Okay, so we can continue. So what we do here is now we have the following. So we know this value here. So we can actually undo D- decoding over there. And we also know the value over here. So we have U3. We have U3 plus U7. This is equal to 1. So this is equal to 1. So we have a 1 over here. We can undo D+ decoding over there. So it's 4 plus 3. So we have a 4 coming from here. We have a 3 coming from here. We change the sign so it gets a plus 7. Here it's the same. We have a 1 coming here, so we change the sign of this plus 2. So it's minus 2 plus minus 1 is equal to minus 3. So that's the minus decoding over there. Then again, we can do a D plus decoding over this basic transformation to get, there we go. Okay, first we can do the D plus decoding on these basic transformations as well. Here we also have everything that we need. We have this value and this value, and then we can continue. So we have done the D plus decodings in the first stage. Now we can do the D minus decoding, and here I do 2 decoding at a time. So we do the D minus decodings over there. Then you get this value, which is frozen, so you throw it away, and you can ripple through and slowly get the next value. Then you have another bit, and you have this value, so we can undo this basic transformation, and you get this value, this value. Now you can undo this basic transformation. You get, so you see that the value gets larger and larger, so the decision starts to get very reliable. So you get a U4 hat over here. And finally, you have an extremely reliable, and this is the channel gamma plus plus plus. So this is supposed to be the most reliable channel. So that's giving you a very, very nice decision. And we have recovered all the code bits. So that's how you can do the decoding. And that's how the decoding is being done in a successive cancellation decoder. And you see it's a serial step. You need to do some things you can parallelize, but you need to do it serially. So there is also a way of doing this not serially, and that's by taking a look at the tenor graph of polar codes. We can also build a tenor graph of polar codes. And to do this, let's take a look at the graph. So we have the following situation. I need to fix quickly a different color. So let's do this. That should do the trick. That should do the trick. So we need to define some different nodes. The first thing, we assume that this value is frozen and this value is frozen. And we define a node here. Then we have this value and this value. So we can say these are kind of like variable nodes, and we just draw them in the way that they are ordered here. So we have U1, we have U2, then we have U3, and we have U4. So then we can define new nodes here. This is node V1, this is node V2, this is node V3, this is node V4. So we define a node V1, define a node V2, define a node V3, and we define a node V4. So how are these nodes related to each other? So we know that U1, you can see this, U1 plus U2 is equal to V1. So we can connect them using a check node. So we can draw a check node. we have a check node stating that U1 plus, what did I say, U2 is equal to V1. That's the first check node. Then V2, we say that U3 plus U4 is equal to V2. Okay, so we can draw a second check node. That's U3 plus U4 is equal to V2. We have our second check node. Then V3 is equal to U2. So V3 is equal to U2. Which means U2 plus V3 must be equal to 0. So if U2 plus U3 is equal to 0, we can put a check node. So despite the fact that there is a variable node here, the fact that U2 and V3 are being equal means that their sum must be equal to 0. Otherwise, they cannot be equal. So we can also put a check node. U2 is equal to V3 means U2 plus V3 is equal to 0. So U2 plus V3 is equal to 0 is equivalent to saying that U2 is equal to V3. That's equivalent. And then finally, we have U4 is equal to V4. So we have U4 being equal to V4. That's it. Okay, so now we have some more nodes. We have nodes over here, W1, W2, W3, W4. And we can draw these nodes as well. We have W1, W2, W3, and W4. And again, we have check nodes. So W1 is equal to V1 plus V2. So we can put a check node here. So the check node stating that V1 plus V2 is equal to W1. Then V2 is equal to W2. So I put a check node saying that V2 is equal to W2. There we go. V3 is equal to W3 plus V4. And finally, V4 is equal to W4. So we have constructed a tenor graph, and we see that we have 4 types of variable nodes. So before we can do message passing on this tenor graph, which we can, we need to define what is the channel-related LLR of the different messages. So therefore, we define 4 types of variable nodes. The first one is the green one. That's the channel variable node, because the messages W, they are connected to the channel. The output of W is transmitted over the channel and it's received as Y1. So this is a channel variable node. And so we can put the channel-related log likelihood ratio as an input to this channel variable node. So here we have L of Y1 given X1. We have L of Y2 given X2. we have L of y3 given x3. And finally, we have L of y4 given x4. So these are connected to the channel, and they get the channel log likelihood ratio. So what do the other variable nodes get? So let's look at the blue ones. The blue one is a hidden variable node. It's not connected to the channel. We don't make an observation for this variable node. And so we don't know its value, which means we have to assume it is erased. And if it's erased, the channel-related log likelihood ratio of this guy is equal to 0. So this one, they will get a 0 from as a channel message. So then we're looking at the frozen positions. So we have the frozen variable nodes. They are known. They are fully known. We know their value. So we can put plus infinity because we assume that the frozen bits are chosen to be equal to 0. So we can put a plus infinity over there. So I'm going to put this in red, plus infinity, and we have plus infinity over there. And then we have the orange variable nodes. The orange variable nodes, they are the unknown information bits. They are actually the ones we would like to know. So these are the unknown information variable nodes. And they are erased as well because we don't know their value. We don't know how they look like because we have a non-systematic code. So we don't know their value. So we have to assume that they are erased as well. So we put a 0 as a channel related log likelihood ratio. So now we have a tenor graph, and in principle we can do decoding of this tenor graph. So we can take our sum product algorithm and we can do decoding, do some iterations, multiple iterations, and finally recover these the information variable nodes at the end, and we have done the decoding. And this actually works pretty well. You can use a state-of-the-art LDPC decoder and just feed the different parity-check matrix and make sure that some of the variable nodes are initialized with 0 channel related LLRs, and some are initialized with infinity. So we can also simplify the tenor graph of the polar code and do the simplification. This is what we're going to do next. There's a word of caution. Polar codes are capacity achieving only with successive cancellation decoding. If we use a different type of decoder, not the successive cancellation decoder, then this will not work anymore, or they are not capacity achieving, or not necessarily capacity achieving. Because the proof of capacity achievingness of the polar codes depends on the syntactic subchannels. The syntactic subchannels, they are chosen based on the successive cancellation decoder, on this D plus D minus decoding. Now, if we do this different type of decoding, we are not necessary that the subchannels behave in the same way, and we're not necessary that they are polarizing that nicely. So we cannot be sure that this is capacity achieving, but in practice it turns out that this works also pretty well. Also, the bits that you need to freeze may be different for this tenor graph based decoding than they are for the successive cancellation decoder. So how can we simplify this decoding algorithm? So in order to do this, let's copy our graph. So let me just see if I can copy everything to the next slide. And here we go. And we're going to do some simplifications. I'm going to do this a little bit. So I'm just going to move this a little bit further. There we go. Okay, so how can we simplify the graph? So the first thing we can do is we can remove the frozen variable nodes and their connected edges, because plus infinity does not change the CN update. So to see this, we have a check node. One of the incoming messages is plus infinity, and this message, so we have two incoming messages. This is mu from V to C, and we calculate the outgoing message mu from C to V is equal to 2 times hyperbolic tangent inverse times hyperbolic tangent of mu V to C divided by 2 times hyperbolic tangent of infinity divided by 2. Infinity divided by 2 is infinity, and this hyperbolic tangent will be equal to 1. So this has no effect on the computation of the check node. So it means we can remove the edges and the variable node and the corresponding edges. Okay, so let's do this. We remove these guys. They will have no effect on the decoding. Okay, so first simplification done. Next. So we go to next page, copy this, and then we start to look at the second simplification. So the second simplification is the one that, so looking at the following situation. So we have a degree 1 channel variable node that is connected to a degree 2 check node. So we have a check node of degree 2, and one of the connected variable nodes is a degree 1 channel variable node, because they are all of degree 1. If you look here, they are all of degree 1. So, and we have an input message that is L. And when we look at the outgoing message that this check node computes, the outgoing message that it computes, so mu C to V, is just going to be equal to L. So it's 2 times inverse hyperbolic tangent times hyperbolic tangent of L divided by 2. And this is just going to be equal to L. So if this is a variable node that is has 0, is an erased variable node, so it means we can replace this one by just changing the connected variable node to have the log likelihood ratio at its input. So this is a simplification we can do instead of having this awkward situation degree 2 check node with a degree 1 variable node. We can move this degree 1 variable node to the channel related value to this variable node. So let's do this. So here we have one of those. So let's do, we can remove this and then we can add L of y4 given x4 to this variable node. So we remove this one, we remove this, and we remove the assigned check node, and then we can put L of y4 given x4 over here. Do we have another one? So let's check. This one as well is connected to a degree 2 check node. So we can remove that one as well. So this is L of y2 given x2. And here we have L of y2 given x2. Okay, next one, degree 1 variable node, but it's connected to a degree 3 check node. So here it doesn't work. Degree 1 variable node, channel related, but it's connected to a degree 3 check node, so it doesn't work. Okay, so we have simplified those guys. So let's do the next simplification step. So we go one to the next slide so we can see the tenor graph thinning out. So the next step we're going to do is a degree 2 erased variable node. That's a little bit more difficult to see. So degree 2 erased variable node looks like this. So we have a 0 as a channel related LLR. And then we get a message from a check node C1. So mu from C1 to V. And when we calculate an output message, we calculate a message mu from V to C2. And let's take a look at the situation. So now we're looking at the second check node and we calculate the message mu from, this is C1, this is C2. We calculate the message from C2 to some different variable node. So to some variable node Vj. So this is equal to 2 times the hyperbolic tangent inverse times the product, or times first the incoming message that we have here. So first this incoming message. So it's the hyperbolic tangent of mu V to C2 divided by 2 times the product of the hyperbolic tangents of the different messages. And I just call them Li divided by 2. These are the other messages that we don't know. So now what is mu from V to C2? If we do the variable node update, this guy is equal to mu of C1 to V. That's the message that check node C1 sends to this variable node. So we can insert this message in the update equation. So instead of having mu from V to C2, we can now say this is equal to mu of C1 going to V. So what is mu of C1 going to V? So mu of C1 going to V essentially is, so mu of C1 going to V essentially is 2 times the inverse hyperbolic tangent of the product of the other connections, so some other connections. And I just say this is a product of the hyperbolic tangent of Lj divided by 2. So these are all the other connections that this check node has. So now if we apply the hyperbolic tangent to this function, so apply the hyperbolic tangent, so we divide this by 2, this 2 cancels, we apply the hyperbolic tangent, then this, the inverse hyperbolic tangent cancels, and we finally have that mu of C2 given Vj is equal to 2 times the inverse hyperbolic tangent of the product of the j, hyperbolic tangent Lj divided by 2, times the product over the i's, hyperbolic tangent Li divided by 2. So essentially the output that we have here depends on all the other edges that come to this node except this one. So all the other edges plus all these other edges. So it means essentially we can merge the check node. So what we can do is we can remove the variable node and merge the check nodes. So this is what we actually can do. So can we find such a variable node? Yes, there are 2 of these. We're not looking at those. We're only looking at the blue ones because we need those here. These are our information variable nodes. So we don't want to remove those. We want to keep those because this is where we get the information. But we can take a look at this guy, and it means this guy can be removed and we can merge the check nodes. So let's mark these check nodes so that we will know the check nodes. So we need to merge the check nodes, meaning that this connection over here needs to go to the check node that remains. So for simplicity, this one has just a single connection, so we keep that one. So it means we take this this edge, and this is the edge that we're going to remove. This is the edge that we're going to remove. So this edge needs to go to the new check node. So we remove this edge over here, and we put this edge to this check node. Okay, and now we can remove the check node and the assigned variable node. So we remove this one is removed, and this edge is removed. Okay. And now we undo the marking of our check node. Okay, we have one more. So this one, it's the same situation. So let's mark the 2 check nodes. And we're going to merge this check node. So we're going to merge this check node into that check node. So it means that we take this edge and we move it to that check node. So this edge is going to be removed. And we're going to put an edge. No, this needs to stay. So we're going to put an edge to this check node. And then we can remove this guy. And we can remove this variable node. Okay, and then we remove the marking. Okay, so now we have a simplified, tenor graph. So we can actually take this tenor graph and we can redraw it that is such that it becomes a little bit clearer. So what we can do is we redraw. So we have the two information variable nodes. We keep those U1 and U4. And then we have the channel related variable nodes. So we have L of Y2 given X2. We have L of Y4 given X4. We have L of Y1 given X1. And we have L of Y3 given X3. So and then we can draw some, we can draw the connections. So we have undone the merged check nodes, so we draw them. It's almost there. So we have 4 check nodes left, and here we go. So U2 is connected to check node 3. So this is U2 and not U1, sorry. Connected to check node 3 and check node 4. U4 is connected to check nodes 1 and 2. Then this one is connected to check node 1 and check node 3. This one is connected to check node 2 and check node 4. This one is connected to check node 3 only. And this one is connected to check node 4 only. Okay, so this is the tenor graph of our code. And we have 2 unknown variable nodes. And then we can do message passing. So we can do message passing between these variable nodes and these check nodes. And after some round of message passing, we can make a decision on U2 and U4. And this will give us our final decision on these 4 bits. So it means we can use our graph-based coding framework to decode polar codes. So essentially all the polar codes that are, for instance, in the 5G standard can be decoded also with this framework, which is very nice because it pulls everything under one big umbrella that we have. Okay, so to summarize, polar codes are an information theoretic approach to coding, not an coding base, but it comes essentially from information theory, trying to generate new channels with a higher and a lower mutual information. What we do is we construct equivalent channels that polarize. So they are either perfectly reliable, perfectly unreliable. We only transmit the information on the reliable channels. We transmit garbage data, so-called frozen values, on the unreliable channels. Then we have a successive decoding. which enables us to recover the reliable channels. We need very, very long code lengths n needed for efficient polarization. So the length of the code must be very large. Interestingly, with different types of decoders, the so-called successive cancellation list decoder, polar codes are also very, very good for short block lengths. But with the successive cancellation out-of-the-box decoder, you need very long block lengths. The complexities are in the order of n log n. This is a little bit disadvantageous compared to LEPC codes, where you have O of n. However, you need to do multiple iterations, and as a ballpark number, the number of iterations is log n, then they are more or less in the same ballpark in terms of complexity. Polar codes are still being actively researched on, so finding good decoder is not trivial. There are many variations of decoders, for instance, using belief propagation decoder based on a simplified tenor graph, using different other decoders, successive cancellation with list decoders that are they are part of active research to improve the decoding performance or reduce the complexity at the same time. So this concludes this chapter, and this also concludes the whole lecture. So with this, I'm very happy and hope you have enjoyed the lecture. And with this, I like to wish you good luck for the upcoming exams.